matrix A can be a square matrix. A square matrix A can be decomposed into V and lambda. V is the eigenvector matrix and lambda is the eigenvalue matrix. Right? A is equal to V lambda V inverse. That's the decomposition. A can be decomposed as V lambda V inverse. When you multiply these three matrices, you get A. Provided the vectors in the V matrix are eigenvectors and the values in the lambda matrix are eigenvalues. The diagonal values in the the lambda matrix is eigenvalues. What is eigenvector and what is eigenvalue? Characteristic vectors, we call them as eigenvectors are characteristic vectors. Okay, latent vectors are characteristic equations. But eigen means characteristic. So characteristic vectors means there must be some quality to the matrix, and when you decompose it, the decomposition will carry the essence of the matrix. There should be some meaning to the matrix. When you decompose it, the decomposition will carry the essence of that matrix. Got it? If you take a covariance matrix, the decomposition will have, these vectors will have the covariance essence into them. If the matrix is a co-occurrence matrix, in NLP we will get co-occurrence matrix. There is some meaning, right? The covariance or correlation matrix has got some meaning to the matrix. And when we decomposed it, we have got covariance into the vectors. So that point is very important. Whichever characteristic the matrix is having, that characteristic will be extracted into the eigenvectors, and the eigenvalues will quantify which vector extracted how much quantity. Which vector extracted how much quantity will be denoted by these eigenvalues. Okay, so that is the key point. And now when you look at the dimensionality reduction, the matrix is not a square matrix. First point is the data set is not a square matrix, and we are trying to extract the covariance from the data set. Obviously, before we apply eigenvector eigenvalue decomposition, we should be converting this matrix into a square matrix. First thing, matrix point of view, the linear algebraic point of view, if you want to apply eigenvectors. Why do you want to apply eigenvectors? You want to extract the essence from this data set and try to create a smaller data set. Right? That's our goal. Dimensionality reduction is taking a bigger data set, or with big high dimensionality, and reducing it to a lower dimensionality. Right? So this dimensionality reduction technique is basically trying to extract the essence and reduce it, because if you eliminate 10 columns from this data, or maybe 100 columns, or maybe 1000 columns, you will lose the essence of the data. Okay? The essence also we are trying to extract. The dimensionality reduction technique principal component analysis assumption is that the whole essence of the data is present in covariance of the data. Okay. The principal component analysis assumption is that the whole essence of the data is present in the covariance of between the input columns. Right? That's where it is trying to extract the covariance essence from the data set. Sisiram Garu. Yesterday you are trying to point that out, right? So why covariance, right? Why covariance? There may be other features which are having more importance, right? But PCA's capability, or PCA's basic assumption is that it can extract only the covariance from the data. Okay. So instead of eliminating columns, we are trying to extract the essence and create new set of columns. X1, X2, and so on, X 100,000 is converted to X1, X2, and so on, Z1, Z2, and so on, Z100. How it happens? Data is taken, mean centered it, right? And then we find the eigenvectors for the covariance matrix of the original matrix. Okay, covariance matrix of the original data. How will we do that? Take the data, mean center it, right? Then calculate x transpose x so that you get covariance matrix. Using, on this covariance matrix, we are applying eigenvector decomposition. That is creating, that's creating, 5 by 5 matrix because there are 5 columns. There are 5 columns, so it's creating 5 by 5 matrix. Give me one second. So 5 by 5 matrix it is creating. Okay, and for each eigenvector we have eigenvalue. So that is how PCA works. And then yesterday we looked into the code. There, it should be a bit more clear. So on image processing also, previously people used to apply PCA to reduce dimensionality and then build machine learning models. Are you getting the point? You apply PCA, right, on an image processing, so there are images. Images will be of 3 dimensions, right? 500 by 500 by 3 or 200 by 200 by 3. The color picture is going to have 3 dimensions. This is a black and white picture, right? That's where it has got only 28 by 28. Right? If it is a color picture, right, you will have 28 by 28 by 3 channels, RGB, red, green, blue. 28 by 28, a 3-dimensional matrix, with 28 by 28 rows and columns. Okay, so in NumPy, right, it will be like this. Right? Channels first we call it as 3 by 28 by 28. Okay, so if there is a matrix with 3 by 28 by 28, there is going to be 2352 number of columns, 2352 pixels in each image, right? If the handwritten digit is a color picture, then it would have had 2352 pixels. Do you agree? You agree, right? Can you see the screen? I am showing calculator basically.
Yes, sir.
Yes.
Very
So this is going to be high dimensional space. If it is like, if it is like 100 by 100 by 3 also, right? 30,000 columns, right? So you need to reduce the dimensionality in order to apply machine learning algorithms. In deep learning algorithms, even if the dimensionality is high, it can handle. But machine learning algorithms, it cannot handle high dimensional space, right? That's where to reduce the dimensionality, they used to apply PCA and then reduce the image, image dimensionality and then build model. So if you look at there will be some examples, where this is not needed now. This is not needed now, but I am just trying to show how it was used on image processing, because IIIT Hyderabad is still trying to explain the same concept. I don't know why. Uh, See that This is a color image, original color image. When I apply PCA, it becomes like this. Okay. There is faces also. The PCA on faces. Yeah, see this. See this, if you pass the original image, right, after applying PCA, it becomes like this. And the image gets damaged. But it'll carry the pattern. What pattern it will carry? The relationship between input variables, right? The three, I had 30,000 columns, right? 30,000 columns. Between them, it will carry the K fold. We'll see the fold also in a minute. Right? They took this image and they applied PCA and the data became like this. Dimensionality reduced and it became like this. You apply PCA on all images and then try to take that reduced dimensionality data and build a model to identify, classify the picture, right? Who is that person? Right? Object detection. Sorry, the face detection model. But this is not needed now because we are going to look into deep learning. That's not needed now. So I'm trying to show one example there, right? So we took PCA and then did fit transform and we have got same number of rows and same number of columns. I said that 784 columns you pass, it is going to reduce the dimensionality, but it did not. Do you remember why? I explained yesterday, right? Do you remember why? When I did fit transform, it still gave the same 784 columns.
We are taking all the components.
Yeah, n components is equal to 1 it is. N component is equal to 1.0 if you give. By default, n components is equal to 1.0. And 1.0 means 100%. You are taking all the components. All components means you took all components and multiplied your data. Right, like this. Right? You took 3 components here, you got 3. If you take 5, you get 5. Right? Like that it is. Okay. And then there are 2 attributes, components underscore and explained variance ratio underscore. In interviews, they'll ask, how will you know that how many components you should be taking? Explained variance ratio is the array which gives you how many components to take. So how many components combined together, the sum of how many components is giving you the desired explained variance ratio, right? If you want only 95%, you take till 95% only. Maybe 150 columns, 150 PCAs. Principal components may be useful, right? So here, if you take 300 principal components, it is giving you the 0.98. So it is a cumulative sum of all these numbers till 300. So you take till 300. If you say n components is equal to 300, right, it will get 98% of the variance in the data. So you can give number also, how many components you want also you can specify, 20, or you can specify the 0.95. Right? This is like 95%, the explained variance ratio I want. So it's going to take, it's going to do a logic like this. Somewhere I have written. Yeah, a logic like this. So argmax of cumulative sum greater than or equal to, right? Greater than or equal to 0.95 plus 1. Right? Wherever this condition is satisfied, that index it will get. Right? Number of components. So that index is 330. Right? 330 principal components you need to take. Give me a second. Give me a second. Yeah. So 330 components we have to take, or n components is equal to 330. We need to specify. How did I know? Right, by looking at this, by using this code. So internally, right, when I say when I say n components is equal to 0.95, right? N component is equal to 0.95. Internally, PCA is actually doing this. It is building the model, right, and finding out all the principal components and keeping eigenvalues, eigenvectors. It is taking all the eigenvalues and calculating this part, and then knowing how many components, and then it is extracting that many components there. Got it? How this is happening internally, I just tried to show. Even if you don't understand, that's okay. But n components is equal to 0.95 will give you 95% of the explained variance ratio from the data set. So this will, right, these 154 Zs, they are not X's, they are not pixels, actual pixels. But still, if you try to reproduce the image, right, it will kind of reproduce it. I'll show in a moment. Okay, so here there is another way. Approach one is to there is another way we can actually know how many components we should be extracting. Approach one is to take it like this, and the other approach is you can do a learning curve, right? You take the length of the cumulative, cumulative sum you took, right? So first principal component 0.95, 0.96, second one a little more, like that, right? So when you add cumulatively, when you add these numbers cumulatively, right, this is cumulative sum, right? See this, it is raising this number, this number, this number, this number. See that it is raising because we are cumulatively adding those numbers, right? So you can actually take a graph of that, and where exactly it meets 100, that you can take that many components. So I am thinking like maybe around 350 it actually met 100, right? One, but I took 400 for safety. So n components is equal to 400 I have taken. So by looking at learning curve, right, you know how much explained variance ratio was extracted by how many principal components, you know it, right? So you can take n components is equal to 400. Got it? In this particular example, it is 400, but other data set, right, it may differ. So n components is equal to 400. I took, and then built a model, just created an object there, and then took that object and that did fit transform of x only, no y. Now you see your data set converted to 400 columns. Okay, so I am going to take this 400 columns data, right? This is a 400 columns data, right? And then inverse transform. There is a function called as inverse transform. What am I doing? I took these 400 columns, right, and then regenerating 784 columns. I shrinked the data, and I'm trying to reproduce the data. So one point we need to remember is when you converted your data using PCA, you will not be able to reproduce it back. But there is some math it is doing. It will try to reproduce it, but we can actually use this as a validation technique also. How good the model understood the data and kind of extracted the essence and created new data can be understood by reproducing it and calculating error between it. Okay. Did you get what is happening in inverse transform? Any questions there? No? Yes. Okay. I can move on, right? Okay. So the dimensionality reduced to 400, and using inverse transform method, I reproduced, right? I reproduced 784 columns so that I can actually generate the image and see how it looks like. If you look at this here, I've taken an index 13,361, some digit, right? I reshaped it to 28 by 28, and then I took the same index from the reconstructed data. Right? This is the PCA applied data. And this is PCA applied data. And then using that same PCA applied data, right, we reconstructed the original data. Right? Both have got 784 pixels, so I can convert both of them to 28 by 28, and I tried to print the image. See this, the reconstructed image is like this. Okay, so when you apply PCA, some amount of data will be lost. That's the point we need to understand. Okay, we will never get the same original data back once you apply PCA. Okay, but this is one technique that actually helps machine learning algorithms work with models. With high dimensionality machine learning algorithms cannot work, but deep learning algorithms can work. Okay, so we need to understand the technique, because when the data set is too small and there are no other models, already pre-trained models existing, we may have to use machine learning only. For that purpose we are learning. Now I applied, is our dimensionality reduction useful? That's the question, right? We applied dimensionality reduction, reduced it to 400 features, but is that really useful or not? So to check it, right, I took the SGD classifier, right, and then took the dimensionality reduced data as X and original Y, and built a model. Right? I reduce the dimensionality, and again I am building my same old classification model, and now predicting and trying to see how it's working. On reduced data, when we built a model, I got 92% accuracy on F1 score on the classification problem. So if we look at the original binary class, I think multi-class. Where is multi-class? Binary classification, yes. See, on original data, when we built a model, F1 score is 92, I think. Yeah. See, F1 score is 92. Okay. On PCA applied data is also 92. That means the most strongly correlated columns in the input space are the most predictive power, the features which have got most predictive power on this particular data. Okay. On this handwritten digits data, the PCA worked. Right? We took 100% of the explained variance ratio into the reduced dimensionality data set, and then built a model with that. We have got 92% accuracy. That means we can use PCA. We can actually apply PCA on this data and then build a model which actually improves performance. Right? Multi-collinearity will be reduced and performance will improve. Right? On the same processor and RAM, you can actually handle more data because number of columns got reduced. Did you get the point there? Any questions?
So you made a statement like multi-collinearity will be reduced.
Yeah, gone basically. Multi-collinearity will be gone. In this 400, right? Multi-collinearity will not be there. Is there a question there on that point?
Yeah, like the same thing yesterday we discussed. We are actually considering the multi-collinear columns.
See, PCA is extracting the essence of multi-collinear columns. Once it extracts, right, it creates independent columns. X1, X2, and so on, X784 have got multi-collinearity, but Z1, Z2, and so on, Z400 are independent. They will not be multi-collinear. It is clear, right? Whatever the essence is there in the data, it will extract and put it into individual columns, independent individual columns. Z1, Z2, and so on, Z400 are independent.
Okay.
Okay. Okay. So incremental PCA. I think any questions? We are done with PCA basically. Right. I'm moving on to the more advanced concepts like kernel PCA, incremental PCA. I will not discuss more.
So there is one question, sir.
Yeah.
In between, we said like we will once we apply or once we calculate uh, the matrix. Just for
Should I go back to the?
just go. Yeah. Notes. So here it's come down. Yeah.
I
This
think I
X1
should put
X2.
slide numbers maybe. Slide numbers will be convenient for you to talk, right? So yeah. Should I
Once we
go
apply
back?
the X transpose, we said that is actually a square matrix.
Yeah, there is a small correction there. XX transpose is going to be M by M matrix. X transpose X is going to be N by N matrix. Okay. What is M by M? What is N by N? N by N is column by column. Okay. X transpose X is going to be column by column matrix. Got it? See this? X transpose this is, and I am calculating X transpose X. That's where we got 5 by 5 matrix because X transpose is 5 by M. X is M by 5. You multiply these two, you get 5 by 5. If you do X by X transpose, right, it's going to be M by M. See this? M by 5 and 5 by M. If you multiply M by M matrix, that's going to, that's going to get the covariance between rows, not the columns. So X transpose X is what we take, and then you do decomposition. Yeah, please go ahead. Correct it, right? Got it, right?
Yeah.
Yeah. So yeah, go ahead. That is very important. I am highlighting some points because I'm going to talk about them in a maybe in the next 20 minutes. So X transpose X. Yeah, go ahead. Go ahead. You are asking something. I disturbed.
So we discussed in theory like before applying the PCA, it should be a square matrix. So
But when you look at when you look at code, it is actually not doing anything such thing, right? Such thing is not done here. So it is doing it. Whatever theoretically you got to know here is all being done by PCA, the class. It is centering the data, it is calculating X transpose X, it is calculating eigenvalues, eigenvectors, then it is taking the vectors, multiplying it with the data and generating these 400 columns. The whole thing is done in a single shot. Fit transform did this whole part. This whole thing. From here till here. That whole thing is done in fit transform. This operation is transform. From here it is all fit. From here, right? Doing mean centering, then calculating transpose, then actually trying to calculate X transpose, XC, and then finding out principal components. This is all fit. Right? Based on n components is equal to 400, it is transforming it. That is the transform operation. This is transform operation. Got it? In a single shot, it is done. This one statement.
Yes.
Did all the operation it need to be done. It need to do. Okay.
So one
Clear,
question.
right? Yeah.
So after fit transform, whatever we get, is it Z matrix? In the slide you have Z.
That matrix. Yes, this matrix.
Okay.
So when I said n components is equal to 3, it took 3 PCA, 3 principal components, and multiplied my data, so it got 3 columns. If I say n components is equal to 400, it will take 400 and multiply, and then you get, in this data set maximum you can give n components 5 only, because only 5 columns are there. five principal components are going to be there because 5 columns only.
So this m by 5 matrix is not the covariance matrix, right? It's original data.
Original data, yes. This is covariance.
The covariance matrix is only used for the principal component analysis or for decomposition.
To find the most variant directions are the principal components, we will use the covariance matrix.
Okay. So in the multiplication at the fit.
The point is like, our goal is to extract the covariance from the data set, right? So there should be a way to find out the essence of covariance from the data. So we took covariance matrix and then found out the essence. Using this essence, we are converting our data.
Yeah. So the fit operation is actually using the principal component matrix and the original data.
So like PC is pre-processing, right? It's not a model, it's a pre-processing, right?
You can say, yeah, pre-processing technique. It's a unsupervised technique, yeah. Unsupervised technique that may help some of the models. That may I said, because you see this here on this data set, right? When I reduce it to dimensionality, we are still getting 92% accuracy. That means the PCA is useful on this handwritten digits data set, ministry data set. But on other data set, right, original model may give 95% accuracy. After applying principal component PCA, you may get 80% accuracy. There it is not useful. It's a pre-processing technique. Generally, the unsupervised techniques are used to help supervised algorithms.
Okay.
So this is a help, right? This is a help. Reducing dimensionality is a help for the supervised learning algorithm, which reduces stress on, training the model and retraining the model and predicting the model, whatever results, right? Instead of taking 784 pixels and predicting, it is taking 400 and predicting. The equation size will reduce, right? So the calculation happens faster.
Sir, just for my understanding, so basically the goal of PCA is to take some input and generate the Z matrix and give that as input to some other prediction model or whatever it is, and then get the actual predictions. Is that so, sir?
Yes, sir. Yes, sir. So basically, to reduce stress on or reduce the amount of resources needed on the supervised learning algorithms, we'll use dimensionality reduction. The same technique in CNN, we'll do it in supervised approach. Deep learning techniques are very powerful, but the main problem with deep learning is it needs huge volume of data. If you have huge volume of data, deep learning is the way to solve most of the 99% of the machine learning problems.
So what will be the trade-off, sir, to use the machine learning or the deep learning?
Huge, right? There is huge difference. The first point is that machine learning algorithm cannot work with huge volume of data, right? Even if it works, right, you will see, when we see deep learning, right, it is like, if one person is working on a task, 100 people working on a task, there will be a huge difference, right? If a task should be completed by 100 people and 100 people are there, it will be more efficiently done. That is deep learning. You can put how many people you want on the task in deep learning, but machine learning you cannot. You'll have only one person, whether it is 100 people's task or 10 people task, you'll have only one person or one algorithm working. There you can actually take 100 algorithms and put it in a single shot. So you will see a huge difference there.
The trade-off, when I say it's the number of records, this is the 1 million records. More than that, then we go for deep learning or.
Okay. So how many? Maybe 100,000, 200,000 records you have, you can go to deep learning. Till 100,000, it is okay to use machine learning. Beyond it, right, we can go to deep learning. And after building model, we'll know. Basically, after building model, this model, that model, right, we'll know. But if you have million records and more, right, definitely we should go to deep learning.
Sir, if our data set has very less columns, means like 10 or 20 columns, then PCA's technique is not
No,
required.
no need,
No need, no
no
need. Yeah.
use. Okay. So there is another concept called as incremental PCA, right? Incremental PCA means it actually takes batch by batch. If I say batch size is equal to 100, now the incremental PCA will actually take 100 records at a time, right? So I am splitting the data, right? There is a method called as array split in NumPy, which takes the data, right? The total data, 33,600 records, and splits that into 100 batches each. And each batch it is passing into the incremental PCA as partial fit. Instead of using fit method, incremental PCA will have partial fit. It will do all the partial fits. Once after understanding the pattern, right, it will do transform. Okay, and if your data set is too huge, right, more than 1 million records, you should be doing incremental PCA and then transforming. But while transforming, right, again it needs huge volume of memory. So I don't know whether it will fit or not. So memory is the major issue in machine learning, but deep learning solves that problem. And we have supervised dimensionality reduction technique. In CNN, we'll do supervised dimensionality reduction technique also. Okay, so incremental PCA uses SVD, the concept. Oh, I forgot the name of. Let me see. Incremental PCA uses. There is a mathematical concept called as singular value decomposition. I'll explain, but there is a okay. I forgot the name of that mathematical concept. Incremental PCA uses that truncated SVD. Okay. Truncated singular value decomposition. So we'll see singular value decomposition as a mathematical technique. If you look at this, right, they say linear dimensional reduction, using singular value decomposition. They are saying I am explaining. I explained all principal component analysis. Sorry, eigenvalue decomposition, right? So far for PCA, I said eigenvalue decomposition. There is another mathematical concept we need to cover. I'll go into that, but before that, right, I'm trying to explain you a simple thing, right? See this, it says, in your API, it says using singular value decomposition. It is not saying the eigenvalue decomposition. Okay. I'll show you the difference between singular value decomposition and eigenvalue decomposition. Okay, in a moment. So this incremental PCA uses truncated SVD, which is a mathematical concept which actually takes small chunks of data and tries to build the SVD and does whatever, right? So ultimately whatever we saw is the correct thing, right? This eigenvalue decomposition and all that is correct. Okay, so let me jump into singular value decomposition. Okay? This term is used. Eigenvalue decomposition is not used. In the term is not used in the theory. They all say singular value decomposition. Here it is truncated SVD. Okay? So if the data is huge, right, it is going to use truncated SVD and try to find out the components and then does the transformation. Right? Multiply the components with the data and transformation. So they say SVD. What is SVD? We'll understand. So we understood eigenvalue decomposition, right? So SVD is a magnified version of eigenvalue decomposition, or a little more, technically termed version of eigenvalue decomposition. So here, right, in our current example, what I said was we will take a covariance matrix and then apply eigenvalue decomposition. Okay, that is equivalent to doing singular value decomposition, because singular value decomposition is nothing but eigenvalue decomposition magnified. In real time, your matrices are not going to be square matrices, right? Your matrices are not going to be square matrices. There are two ways to get your matrix into square matrix: C transpose C or C transpose. Suppose that C is your matrix, right? C transpose C will give you covariance between columns, right? If the matrix is a centered matrix, you know what is mean centering, right? If the matrix C is a mean centered matrix, C transpose C will give you covariance between columns. Is that statement right? C transpose C will give you covariance matrix of columns. Is that statement right?
Yes, yes.
So C transpose will give you covariance matrix of rows. Is that statement right? M by M matrix this is, right? This is N by N matrix. The outcome of C transpose C is N by N. The outcome of C transpose is M by M, right? Agreed? No?
Yes, sir.
Good, right? So we can decompose this matrix and this matrix, right? We decompose C transpose C for PCA, right? XC transpose XR, C transpose C, notation change, that's it. C transpose C we decomposed in our principal component analysis, right? But singular value decomposition can take any matrix and decompose it. In PCA, the major requirement is that the matrix should be square. So to find out, to bring down to a square matrix and get a meaning to the matrix, we took the covariance matrix C transpose C. But in most of the cases, the matrices are rectangular matrices. So SVD can handle any matrix. That's the theory. Okay. So let us see how it can handle. Basically, it is doing what we did only, but in a more tricky way. They actually made it a little trick, and then trying to say that it is something big. It is not big. Whatever we saw is the same thing. Stick to eigenvalue decomposition only. I'll explain you singular value decomposition in a simpler way. So if a matrix is not a square matrix, the eigen decomposition is not defined. Right? If a matrix is not square, the eigen decomposition is not defined, and we must use singular value decomposition. No, this statement is wrong. Basically, the statement I got it from the whatever the theoretical books or whatever, right? The statement is wrong. We are doing the same thing. Singular value decomposition is not doing something big. It is actually doing eigenvalue decomposition only, but the statement is wrong. Okay, in a way they are trying to trick. Okay, so just look at that and remember whatever I said. I'll show you what my statement is right. Okay, singular value decomposition can decompose M by N matrix where M is not equal to M. Right? It's a rectangular matrix. That's the statement it makes. Okay, the singular value decomposition provides a way to factor a matrix into singular vectors and singular values. Eigenvectors and eigenvalues only. They named it differently. Okay. The SVD allows us to discover same kind of information as eigen decomposition. Same kind of information as eigen decomposition. Same information as eigen decomposition. Right? Theoretically, they write it like that. However, the SVD is more generally applicable. I don't know why, right? So every real matrix has singular value decomposition, but some is not true with the eigenvalue decomposition. See, if you take any matrix, right, you actually calculate X transpose X or XX transpose, you can do eigenvalue decomposition also. Basically, they are doing that only in SVD. Okay, so the matrix C can be decomposed into U sigma V transpose. Okay, here a matrix A can be decomposed into V lambda V inverse. I said here, right? V lambda V inverse. Okay, that is eigenvalue decomposition. It is a square matrix. Here, what we are saying is a matrix C, right? It's a non-square matrix. It's a rectangular matrix that can be decomposed into U sigma V transpose. C and X are same. C and X are same. In our eigenvalue decomposition, X is denoted as C in singular value decomposition. They are same. Okay. U sigma V transpose. Here the point is we need to remember is U and V are orthogonal matrices. The main difference between the singular value decomposition and the eigenvalue decomposition is U and V are orthogonal matrices. When you decompose your matrix C into U sigma V transpose, you get V U orthogonal matrices. What is orthogonal matrix? I'll explain in a moment. Okay. Sigma is a diagonal matrix with square roots of eigenvalues. Why this is also I'll explain. These 2 points I'll explain in a moment. Okay. What is orthogonal matrix? We'll understand. Orthogonal vector we need to understand first. U and V are said to be orthogonal, if and only if you multiply those two vectors, if you are getting zero vector, right? Zero value, sorry. When you multiply two vectors, what you will get? A number. See this here? You multiply two vectors, you are getting a number. Okay. So when you multiply two vectors, you get 0. That means those two vectors are orthogonal. In a way, they are actually perpendicular to each other. Vector means a line, right? Vector means a data point represented as a line, right? From origin. Do you agree? See, this
Yes,
V1,
yes.
V2 as a data point, and this is a vector, right? If there is a V, minus V1 and V2, that's going to be orthogonal. Minus V1 and V2 will be somewhere here, right? That's going to be orthogonal. That's going to be a perpendicular vector to this one. There are many data points like that, which will be perpendicular to this particular vector, right? So if you find U and V like that, right, then you say those vectors are orthogonal. Got it? Orthogonal vectors. Okay. So if you have a matrix with all, if you have a set of vectors which are orthogonal to each other, then you call that matrix as orthogonal matrix. Okay. So U and V are orthogonal matrices, right? You say the vectors inside V matrix and the vectors inside U matrix are orthogonal to each other. You take any vector from U and V, multiply, you get 0. Those matrices are called as orthogonal matrices. When you apply SVD, the outcome matrices U and V are going to be orthogonal to each other. Okay. So when U inverse is equal to U transpose, U is called as orthogonal matrix again. Okay. So if a matrix has got, right, if a matrix has got vectors inside it in such a way that each vector is orthogonal to other, then U inverse is equal to U transpose. U transpose and U inverse are going to be same. Okay, this point is very important. U inverse and U transpose is going to be same, I said, right? If you look at this eigenvector decomposition, vector decomposition, if U transpose, U inverse and U transpose are same, you can put transpose also here. V sigma, V lambda, V transpose also you can put here. Right? That way they are same. They're kind of similar. Okay. Maybe it takes time. Engulf everything, but let me go through it, and then we'll start for questions or discussion. So this is orthogonal vector and this is orthogonal matrix. U transpose is the inner product. The matrix carries information about pairwise relationship of columns in U, right? U transpose E, sorry, U transpose U. Pairwise relationship in U, same thing, right? XC transpose X, I think down below, I think in other sheet. XC transpose X, what is it carrying? Pairwise relationship between columns only, right? So same thing, right? The columns are mutually orthogonal if and only if U transpose U is diagonal. Let me try to write this in actually. Do I need to understand all this? Maybe, may not be. Right? When we go into deep learning, right, these all concepts are not going to be there. But as a machine learning engineer, as a data scientist, if we have this knowledge, right, that is going to be useful. Either statistical knowledge, basically normal distribution and the other hypothesis testing concepts. If you know them, right, that is good to have. Okay, as a data scientist, definitely in your life you will encounter these concepts. One place or the other. But when we go into deep learning, we are not going to use all these concepts. So even if you don't understand, don't worry. But try to focus, try to learn. Don't be scared. Okay. I took around 3 to 4 months to understand this. I am actually dumping everything in 3 days. Engulf everything is going to be difficult. That is proven. That is actually truth. Okay. Don't be scared. You go through the notes again. Come back with questions. I'll answer. So here, right, I made a statement. The columns are mutually orthogonal if and only if U transpose U is diagonal, right? So suppose that there are matrices like x1, x2, x3, right? There is a matrix. Okay. So this is one vector. This is another vector. This is another vector. I am saying this is an orthogonal matrix. Right? When I say orthogonal matrix, if I do x1 into x2 transpose, what is the outcome? If I say this matrix is orthogonal matrix, x1 into x2 transpose is how much? How much is that value?
0, sir.
0, right? 0, right? So x1 transpose x, x1 transpose x1. What is the value of x1 transpose x1, x2 transpose x2, x3 transpose x3? 0 or non-zero?
So for a diagonal matrix.
Yeah, it's a diagonal matrix. This is not going to be 0. This is definitely not going to be 0. There is some number, right? Multiplication of the vector with itself is not going to be 0. Multiplication of the vector with other vectors in the matrix are going to be 0 because we are saying it's an orthogonal matrix. When I say orthogonal matrix, right, it's going to be like this. This is x1, right? This is going to be x2, right? There is another x3, right? There is going to be another. I think I should have taken other color for the vectors. Right? This is x1. This is x2. And this is. I think there will be another dimension also. If we have 3 columns, right? There are 3 axes. Right? This is x1 axis, the x2 axis, the x3 axis, and then you take this. Right? That's going to be perpendicular to those two. Like that, it is going to be these 3. When I say a matrix is orthogonal, then only it's going to be like this. Normal matrices are not going to be like this. Okay. When it is like this, right? When you multiply U transpose U, you get a diagonal matrix because x1 transpose x1, x2 transpose x2, and x3 transpose x3 are not going to be 0, right? The other values are going to be 0. So it's going to be like this. So some number, sorry, some number, and these are all going to be 0. These are all going to be 0, right? I am actually trying to explain all these because the thought process should change, right? So we should, visualize all this stuff when I am actually talking. Okay. So if you are not able to visualize, also not a problem, because in a single shot you will not get it. It takes time. Okay. But put your effort to understand, because this much content is nowhere given, and they'll not spend time, right? So this is all important. This is all very important. If you are trying to do some research, or when you are learning new concepts, right, there will be mention of these here or there. There will be mention of these. Why am I explaining all this? Because when I started learning AI in 2014-15 time frame, I used to start and go till some extent and find something like this, SVDR, maybe orthogonal vector, orthogonal matrix, and go back to math and get lost there for 2 months and come back, right? By the time I come back, right, there will be new algorithms, new things, right? So it's going to be lots of waste of time. So I am trying to reduce that wastage by inducing all these concepts here, okay? So the columns are linearly dependent if and only if U transpose U is singular matrix, right? The columns are dependent. We actually saw this, right? In our dummy variable trap, we said that X transpose X is going to create a singular matrix if you have strongly correlated columns, right? U transpose U is singular, that means linearly dependent. So these are the two concepts we need to maybe understand a little bit. Any questions here? It's clear, simple thing, right? Any questions here? Good. So we said, when U is an orthogonal matrix, U is an orthogonal matrix, we are saying U inverse is equal to U transpose. If U inverse is equal to U transpose, U transpose U transpose is going to be I, right? U transpose or U inverse is same, right? Like that is going to be I. Okay, these concepts are important. We understood. The value at ij index in U transpose U define how much the two features I and j are correlated. This we saw already. Xc transpose X or whatever, right? The higher the value, the more the two features are correlated. The diagonal values I in the matrix represent the correlation between a feature and itself. It is and. I kept and here and itself. Okay. So the diagonal values are going to be the relationship between the feature and itself. That's not important. Okay. So I think we understood the fundamentals there. Now, right, I am saying the matrix C can be decomposed as U sigma V transpose, right? And saying that U and V are orthogonal matrices, right? I already took that U V are orthogonal matrices. Our goal now is to take a rectangular matrix C and decompose that into U sigma V transpose. Okay, I'm going to make a statement now. This is very important. Just remember and understand. We need to assume that C is already decomposed as U sigma V transpose. Our goal is to decompose the matrix into U sigma V transpose. Okay, our goal is to decompose the C matrix into U sigma V transpose. But what I'm saying is, assume that already the matrix is decomposed into U sigma V transpose, where U and sigma are orthogonal matrices. Okay, U and sigma are orthogonal matrices. When I say U is orthogonal matrix and V is orthogonal matrix, the vectors inside, columns inside U and V, columns inside U are all perpendicular to each other. Columns inside V are all perpendicular to each other inside V only. Inside V, inside U. Okay, that point is clear. That point should be strongly understood. So we are assuming that U and C is already decomposed. Now, if I calculate C, C transpose C, I assumed that already it is decomposed like this. I am calculating C transpose C. What is C? I already assumed it as U sigma V transpose, right? I am putting that here. Right? In place of C, I am using this. Okay, I'll explain why I am actually assuming that, and I'll explain that in a moment. Okay, so I am putting this part. Till here, is that clear? Till this point, is that clear? Can I move on? Shall I take it as yes? Yeah, I am taking it as yes. Right? I actually kept in place of C U sigma V transpose and U sigma V transpose because I already assumed that it is decomposed. Right? So AB transpose is equal to B transpose A transpose. I think somewhere I kept it. So if you try to apply transpose to this, right, this will actually go to front. The V transpose will go to front. Right? U will come this side. Right? This whole transpose, V transpose, whole transpose, U transpose, and sigma transpose. So transpose, whole transpose is going to be V. Right? And say sigma transpose and sigma and V transpose. Right? So if you look at this part, right, U transpose U is going to be I because U is a orthogonal matrix. Right? U is a orthogonal matrix, so it becomes I. When you multiply any matrix with I, you are going to get the same one, right? So sigma transpose sigma is going to be sigma square because sigma is a diagonal matrix. See this diagonal matrix here? Lambda 1, 0, 0, lambda 1. I multiplied 2, right? These sigma and sigma. I got sigma square. Or you transpose this also, you get the same thing. Sigma square only you get. Okay. So V sigma square V transpose. Right? C transpose is actually equal to V sigma square V transpose. If you assume that sigma square is some number or some matrix, how is it looking like? Let me try to. I'll make one statement here. This thing, right? This C transpose C, is that a matrix? Is that a square matrix?
Yes, sir.
Is that right? This is a square matrix, right? If you look at this, right, this looks like, to me, that looks like V lambda V inverse. This looks like this to me. Do you agree? Do you agree? Where lambda is equal to sigma square. Huh? Lambda is equal to sigma square. If I represent lambda is equal to sigma square, does it look like that? Yes, no?
Yes, yes.
Right?
The
So,
V transpose equal to V inverse because that is an orthogonal matrix, right?
yeah, orthogonal matrix, that is one thing, right? That is for sure. But at a high level, right? If you look at it, it looks like this. What is this actually? C transpose C's eigenvalue decomposition is this one, right? C transpose C is a square matrix. If you do eigenvalue decomposition, you get this, right? Do you agree?
Yeah.
Right? So stay there. Okay. C transpose C is a square matrix. If you do eigenvalue decomposition, you get this. Stay there. And it looks like this. And again, V is an orthogonal matrix. You can represent it as transpose or inverse. Right? That point is clear. Okay. If you take C transpose, and I assumed that C is already decomposed as U sigma V transpose, I am substituting that. and then when you apply the transpose, the AB transpose is equal to B transpose A transpose. If you have ABC transpose, right, it's going to be C transpose B transpose A transpose. Okay, so that's what it happened here. So V transpose whole transpose, sigma transpose, and whatever U transpose, right? V transpose V is going to be I. Sigma transpose is going to be sigma square. U sigma V transpose. It looks like to me U lambda and U inverse. If you take CC transpose, a square matrix, and apply eigenvalue decomposition, you will be able to find V. If you take CC transpose and apply eigen decomposition, you will be able to find U and sigma, lambda, right? Right, lambda is nothing but square of your eigenvalues. So apply square root of the values here, right? Then you get sigma also. So you can actually find V sigma U by calculating eigenvalue decompositions to C transpose C and C transpose. Done. Singular value decomposition is done. Let me recap a little bit, and I'll stop, and I'll So our goal is to decompose a rectangular matrix into U sigma V transpose, where U and V are orthogonal matrices. That's our goal. Okay. To achieve, right, what we need to achieve, you need to find U, sigma, and V. You get C, a rectangular matrix. You need to find U, sigma, and V. To find that out, you need to take C transpose C, apply eigenvalue decomposition, CC transpose, apply eigenvalue decomposition. You will be able to find V, sigma square, and U. You apply square root to the values of those sigma square, you get sigma. Did we got the decomposed matrices U, V, and sigma? Got it or confused? Basically, we are doing eigenvalue decomposition only for C transpose C and CC transpose to find out U, sigma, and V. The same concept is again used in word vectorization, word embedding, they call it as. Okay. If you understand this here, right, there it's going to be easy. Got it? Any questions there? Even if you don't understand anything else, nothing here, I'll start from scratch. Maybe that is more confusing. Got it?
So one question.
Yeah, please.
So here we assumed C as a non-square matrix, and C transpose C is converted to a square matrix.
Yes.
Yeah, but the same thing we did in eigen decomposition also, right? X transpose X gave us.
That's what I'm saying. Singular value decomposition is a small trick. The only trick here is that U and V are orthogonal matrices. That's the main key. If U and V are not orthogonal matrices, right, you will not be able to decompose. When you decompose a rectangular matrix into three matrices, definitely U and V will come as orthogonal matrices only. If they are not orthogonal matrices, you cannot decompose because you will get stuck here. This will not become I, right? That will not actually derive to a form where eigen decomposition can actually bring down to, right?
Yes.
So that's the trick. That's the simple trick. Basically, you can actually even in the PCA, you are taking C transpose C and doing it. There it makes sense because you are trying to extract covariance, and the covariance matrix is coming by doing centering, mean centering, and C transpose C. But any matrix without mean centering or anything, you can actually decompose that into three matrices. Why do you need to decompose? I'll talk about that when we see the word vectorization concept, right? We'll see that more there. I'm not trying to dump everything at once, because these are all interrelated concepts, and there will be some other concept we need to cover in between. So the structure of the course will actually bring you there. Any questions, or did I interrupt you while asking questions?
No, sir, clear. So in eigen decomposition, we are calculating only one eigenvector, but here we will be calculating two eigenvectors. Like that we can.
No. This is a matrix actually. In a matrix, you will have more vectors. B is a matrix and U is a matrix, right? Here, there it is V transpose, V inverse, V lambda V inverse. Here it is U V, two matrices. Yeah, that is good. By 2, this is column wise relationship extraction. This is row wise relationship extraction. U will hold row wise relationship extraction. We will hold the column relation extraction. There will be row relation extraction also, right? There will be relationship between rows also. Basically,
yes,
when
because
you
it is not square matrix, right? So we have to extract covariance between
when
rows
when you look at kernel trick, right? It is trying to extract row relation. Right? That is one way. That's one way of doing it. This is another way of doing it. Row relation extraction is captured into U, the vectors in U. Column relation extraction is captured into vectors of V. This is very important point. This is the point we are going to use in the word vectorization. Row relation extraction and column relation extraction. No, that's the point we are going to use there. But in PCA, our main goal is column relation extraction. There, it definitely uses eigenvalue decomposition only. Even if you do singular value decomposition, right, you are going to take V, vectors in V. You are not going to consider U, right? In theory, they wrote it as SVD, right, singular value decomposition. But in the singular value decomposition, they're going to take the V matrix into consideration. U they'll ignore, because V is the one which is extracting the essence from columns. No need to do SVD. You can do eigenvalue decomposition, right? So it is a simple thing. You take the central mean centering and then do. So I am trying to the internals, right? If you know how eigenvalue decomposition works, how SVD works, you will know why they considered V only, not U. They'll ignore U. They'll consider V. And in the V, you will have principal components. In sigma square it is, but you apply square root to it and take the values, and then they are normalized values basically. And then depending on the importance, you will take the values from there. Okay. So in theory, they write it as singular value decomposition. You can say eigenvalue decomposition also. You got it, right? Why I am saying both are same? Got it, right? Yeah, I was actually confused a lot, initially, and when I looked at eigenvalue decomposition, it looks like makes sense PCA, but theoretically they were writing SVD. I don't know why, right? So when I looked into SVD clearly, right? SVD, if you don't consider this, right, you will not know why this SVD is working like this. This is the key. You need to assume already it is decomposed. Then you substitute, and you will get a form which looks like eigenvalue decomposition. That's the key. You take a square matrix, another square matrix, do eigenvalue decomposition, you get V, U, and sigma. That's it. In both places you get sigma, same value, sigma square, same values you get. But the V vector and the V matrix and U matrix are going to be different. This is the key. You need to assume that already it is decomposed and substitute, and then you will get that.
Sir, if that is the case, so all the vectors in V, in case of eigen decomposition, are also orthogonal to each other?
I didn't get the question. In V, orthogonal to each other.
So here we are assuming in singular value decomposition, we are assuming U and V both are the vectors inside the matrix U and V are orthogonal.
Yes, sir.
So at the end, we are actually some way we are saying it is equal to eigenvalue decomposition.
Yes.
So in eigenvalue decomposition, we are actually getting v lambda v transpose,
Yes, sir.
or v lambda v inverse, right?
Yes, sir.
So there also the vectors inside the V matrix are orthogonal to each other.
Yes, and yes, sir. We can actually test it. Actually, you know, in the I think I never tested. That's a good point, right? We can actually take these principal components here. Let me show you this. PC 784 PCs. These 784 PCs, right? Maybe take two of them and multiply. Maybe I'll do that right away. Give me 1 second. Right, that's a good question. That's a good question. That's a good question. Let me. There is an error. Right, so here what I said was, you know, the vectors inside these components are orthogonal to each other, right? So let me take np dot zero, right? Right, so all columns first row, right? So right, that is the first vector, right? Is that right? Is that correct?
Yeah.
Tuple indicates what? Let me see what is there in this. Oh, okay, shape I took, sorry. See this? 4.33, 10 to the power of minus 19, almost 0. Right? Got it? Got it?
Yes.
It's almost 0, right? So you take any vector from this components and two vectors and multiply, they are orthogonal. Basically, yeah, that's what is going to happen. But as you know, it applies SVD, right? That's where, yeah, basically what our understanding is correct. You're all getting it, right? What Shishiram asked.
Yes, sir.
All are 10 to the power of 19.
Are we trying to verify?
Yeah, whether the vectors in V, whether the vectors in V are orthogonal or not.
Okay.
These are vectors in V only because it's C transpose C or XC transpose XC, right? If it is XX transpose, right, it's going to be U. Okay. So I'm going to stop recording.